So this is going to take you through how particle accelerators actually work and why they're so useful. So you can see here the first slide tells you why we use particle accelerators in terms of discovery, medicine, industry and security. You can read that yourselves later. Easiest type, apart from the Cyclotron tube that you had last week, is what's called a linear accelerator. So here you've got an electron or ion source here, and that's accelerated through these electrodes, and they have a high frequency alternating current, which means that the electrodes go negative positive and then positive negative. And the idea is that the electron or charged particle gets accelerated between those as they flip between going positive and negative, and all the way along they're going faster and faster, so the distance between them has to be greater and they finally hit a target. You don't need to know exactly how it works, just the main thing is that it's a linear because it's going in a line, and it is the alternate, and it's just the fact that you've got an electric field that accelerates the charged particles. Cyclotrons a different thing. And the first thing about cyclotron is when they were first built in the 1960s and 70s, you can see that it's circular in shape. We'll come back to why that is in a moment. And that's a more modern one, which is a proton beam accelerator for medical uses. And inside you can see there's coils of wire, and it's those coils of wire which are used to make magnetic fields. So in the cyclotron, you've got a very large, very strong electromagnet going from north to south there. Inside you've also got these two cavities called Ds, because they're shaped like a letter D, and the magnetic field goes top to bottom through those two D shapes. The D shapes are connected also with an oscillator which has high frequency alternating current to provide an electric field as well. So again, there's the high frequency AC source between the two Ds there. There's one electron magnet, there's the other electron magnet. The idea is that the cyclotron cycles, hence why it's called a cyclotron, the charged particles out, and then they eject and hit a target there at high speed and with high energy. That's it looking from the inside. So again, you can see the charged particle going round and finally out there. The alternating current is there to accelerate the charged particles across the gap as they come out. Generally it's a proton which is accelerated, and each time it crosses then it goes positive to negative and then positive to negative over here. The reason they've got the alternating current there is to swap the polarity between the two Ds. The magnetic field, as you can see, is being shown that it's coming upwards through the Ds there. That's to keep the charged particle in a circular path, because the force on the charged particle is always at right angles to the direction of the motion, and therefore it always pushes it in towards the center like we did last week. So this video, which you can watch later on with sound, explains it really well with a physical model, so that's definitely worth watching because it shows how the particles accelerate between the gap. So key things you would need to know about the cyclotron. Firstly, the electric field is to do with increasing the speed or accelerating the proton, and it's got to be alternating current as it's got to go from one side to the next. All the magnetic field is doing there is keeping the protons actually in that semicircular motion so that it can go backwards, and forwards each time. And because of the equations that you could go on to do in advanced higher physics, the actual time to cover each semicircle is constant, because even though they're going around a faster radius at the end, they're going around a larger radius at the end, they're actually going faster, so the time for each. And then once the radius gets large enough, that's when it escapes and hits the target. So you can see a cyclotron here at Grenoble, which if you've ever been on the ski trip with the school, we actually drive quite close to that as we're going up to the resort in the Alps. A synchrotron is a slightly different thing. This is much larger, and so you can't just use a single electromagnet to produce the magnetic field. So here the charged particles originate in a linear accelerator, they get boosted up in a smaller synchrotron, and then get fired into a much larger storage ring, and that storage ring, they get circulated around many times, and each time they're building up more and more speed, more and more energy. There are such technical terms as a wiggler in the synchrotron, and this time we've got electrons that are going around in this particular synchrotron, and it's got to be a vacuum because the electrons would get disrupted by air particles, and there's electromagnets to bend the electrons in to keep them in a circle. So rather than being a constant magnetic field, they just get bent and then go along like that, bent again, go along like that. And you've got various of injectors to put the particles in, and you can see here as this speed goes around there, the force is in that direction, keeping it in towards the center of the circle. So that's the linear accelerator which injects them into the booster, and then the whole thing is roughly the size of a car park there to make it go round. Of course, this video here shows you how an Italian one works in Trieste. So again, that's just 4 minutes. You can watch that yourself with sound. Key things are, again, the electric fields are accelerating at different parts of the loop. It needs multiple accelerators, so you've not just got the one like you have in a cyclotron. And again, magnetic field is to do with the direction that the charged particles are moving rather than increasing the speed. But both fields need to be changed as the speed increases with the synchrotron. And you can take off the particles at different points that you want there. So of course the most famous and the largest synchrotron in the world is at CERN, the Large Hadron Collider. So you've got a similar summary there, you can read through that yourself. And there's a video to watch about the CERN Large Hadron Collider. You're now going to be asked to work out what the Atlas detector is at the LHC in CERN and work out these 4 questions and produce some slides from that. So in terms of content, we covered those 2 last week in terms of the magnetic field you get from a moving charge and the direction on a charged particle. What we've done today is the basic operation, and it is just basic operation of particle accelerators. The electric fields accelerate, increase the speed and the energy. The magnetic fields contain and keep it in a circle until it goes off to find the target. And it's the high energy collisions which actually produce other particles and give us a real idea of what matter is actually made of.